Okay, this is the 7.3b shape properties guided notes for trapezoids and kites. And let's take a look, see what we have here. So first of all, we have isosceles trapezoids. Let's just talk about those for a second. If we were to take a isosceles triangle, which I kind of put in gold up here, and took the midpoint of each one of those sides, we basically we're dividing each side into two parts. But this original isosceles triangle has congruent base angles, so the angle at D and the angle at C are going to be congruent to each other. Now if I take the mid-segment, or the midpoint, and connect it together, this side is parallel to this side, which sets up this isosceles trapezoid, because this being the midpoint makes this side and this side congruent to each other. If I look at these small triangles, then we can, using this base as a side, and we've got those congruent angles from the isosceles triangle, and then these two links here are going to be congruent because of the A and B being the midpoint of DZ and CZ. That gives us a congruent side. So by side angle side, these two triangles are congruent, which gives us a lot of properties that we can use to get started on about the diagonals in an isosceles trapezoid. Since these two triangles are congruent, AC and BC, these two here are going to be congruent because of corresponding parts of congruent triangles. So that means that the diagonals in an isosceles trapezoid are congruent to each other. And then in a little bit of a different proof, using alternate interior angles in the parallel lines, we can actually prove that these two triangles are congruent to each other. And by doing that, we have that this distance and this distance, where the diagonals intersect each other, gives us an isosceles trapezoid. So there's lots of properties, sort of like of balance, between the diagonals in an isosceles trapezoid. Now in a general trapezoid, a trapezoid is just a quadrilateral with exactly one pair of parallel sides. So we call the parallel sides the base. When we get a chance to do a little bit of algebra on this, we'll actually be looking at, maybe this is base 1, and we'll call this base 2. And at some point we'll be doing areas of these, where we talk about the average of the bases times the height of the figure to get the area, and there's a little proof that goes with that. But in terms of definitions, in a trapezoid, we have opposite pairs of sides are congruent. Exactly one pair of sides are congruent, and I would actually call this the side, and this the other side. In isosceles trapezoids, I got used to calling these the legs. So legs, from my point of view, the way I've learned this, legs only exist in right triangles and isosceles trapezoids. Otherwise, we just have sides of the triangles. So if we draw a diagonal, this trapezoid, because it's a general trapezoid, there's nothing special about the lengths of the diagonals or where they meet or anything like that. But in an isosceles trapezoid, all of these different pieces are congruent because of the isoscelesness of the trapezoid. So let's go on and fill in some of these. So if a trapezoid is isosceles, then each pair of legs is congruent. Okay, if a trapezoid has one pair of congruent base angles, then it is an isosceles trapezoid. So let's look at the diagram for that for a second. So exactly one pair of congruent base angles. So here's a congruent pair of base angles, here's a pair of congruent base angles, these two. So if you have a trapezoid that has exactly one pair of congruent base angles, or has a pair of congruent base angles, it must be an isosceles trapezoid. So it's sort of like the converse idea of the definition of isosceles trapezoid. Okay, a trapezoid is isosceles if and only if its legs are congruent. So if it's got congruent legs and it's a trapezoid, then it's going to be an isosceles trapezoid. And because, again, being isosceles, these angles are going to be congruent, these segments are going to be congruent, these segments are going to be congruent, and also with the parallel lines, which comes from these diagonals here, these angles are going to be congruent, and these other angles here are going to be congruent. So there's a lot of stuff you can do with measures in isosceles trapezoids. Okay, let's look at these examples. Is each trapezoid isosceles? Justify your answer. So let's look at this. This is setting up the parallel lines. We've got 115 degrees. So supplementary, since we have parallel lines cut by transversal, we have these angles are going to be same side interior angles. If we can find that this angle and this angle are congruent to each other, then by the converse idea that we were talking about before, if congruent base angles, then trapezoid is isosceles. So that's what we need to do, is do 180 take away 115, and 180 take away 115 gives us 165, or gives us 65. So this angle is 65 degrees. But 65 isn't congruent to 55, so this is not isosceles. So it's not an isosceles trapezoid. Double check the math here. 6 and 1 is 7, and 5 and 5 makes the 10s. That makes 180. Okay, let's look at number 2. Here they're showing us that these diagonals are congruent to each other, and that these two sides are parallel. Well, from our diagram above, that sets up the pattern that goes with an isosceles trapezoid. This, by segment addition, these two are congruent to these two. You add them together. AC is congruent to BD in the diagram. That's what we have here. Because these are congruent with the parallel lines and the alternate interior angles, we can actually prove that these two sides are congruent to each other, and it is isosceles. So this is an isosceles trapezoid. Because congruent diagonals. Okay. Now let's talk about mid-segments. The mid-segment is defined as a segment that joins the midpoints of a triangle or a quadrilateral. So again, if we were to extend this up, we could kind of see this as a triangle, and then we could do the midpoint of this triangle and get this mid-segment. And the mid-segment is parallel to the third side of the triangle. So that's how we can get that these two are parallel to each other. And then that this piece is going to be equal to this piece, and this piece is equal to this piece. Well, now if we take the bottom half and break it up by its midpoint, there and there, we can call this the mid-segment of this trapezoid. And it's the segment that connects the midpoints of the sides or the legs of the trapezoid. So this is the midpoint. If we did this like T, R, A, P, and let this be M, and say let this be N, we're going to define point M and point N as being the midpoint of PT, segment PT, and the midpoint of segment AR. And when we connect it together, because of mid-segments in triangles, this, well, you know, this is going to be parallel to the third side of the triangle that we could kind of imagine is there. And it's actually going to be the average length of these bases. This is where I started to before, base 2 plus base 1. If we do base 1 plus base 2 divided by 2, we actually have the length of this mid-segment, and then that times the height, or the distance between these two bases, is a formula that we use to find the area of a trapezoid. If we know the mid-segment length and the altitude or the height, then we can calculate the area. So the mid-segment is parallel to the bases, and it is equal, and it is half the sum, which is the average idea, half of the sum of the bases. Yeah, just half the sum of the bases. So I don't think we really need this, but the formula is base 1 plus base 2, half the sum divided by 2 is equal to the mid-segment length, would be equal to mn in this diagram. So b1 plus b2 added together divided by 2 gives us this length. And this is parallel to each one of the bases. Oops, let me go back. Okay, let's move on. In this figure, UR is the mid-segment of trapezoid PQST. Find the length of UR. We're going to add the bases together and take half of that. So we have 11 plus 18, which is 29, and we're going to take half of 11 plus 18, which is 29 divided by 2, which is 14 and a half. 14 and a half times 2 gives us 29. Let's look at number 4. In the figure, JF is the mid-segment of trapezoid DEGH. Find the length of JF. Again, we're going to add the two. Now this trapezoid seems to be like upside down compared to the other one, but same idea. Base 1 now is 19. Base 2 is 34. It all depends on how you define your bases. And the sum of the bases, base 1 plus base 2 divided by 2, is equal to the mid-segment length, which for this one would be JF. So 19 and 34 is 53. 53 divided by 2 comes out to be 26 and a half. So JF equals 26 and a half. We do the same thing over here on this one. We could write UR equals 14 and a half. Okay, let's look at number 5. In the figure, RN is the mid-segment. So here's the mid-segment, and so this one we have to find the length of the base. So say base 2 is missing, that's going to be x, and there we have base 1, and this is the mid-segment length. Our formula for this problem is going to be the length of the mid-segment, Rn, is equal to 1/2 the sum of the bases. Base 1 is 16.7, and base 2 happens to be x. So we're still doing 1/2 the sum of the bases. Now what we have to do with this one is find out what x makes this work out. Now they're also telling us that the length of Rn is 24. So we have 24 is equal to, and let me write this as a fraction, 16.7 plus x divided by 2. So here's base 1 plus base 2 divided by 2 is equal to the length of the mid-segment. So to simplify this, I got to bust x out of this fraction. It's in the numerator. I need to get rid of the denominator first, and then I'm going to subtract the 16.7 to get x by itself. So I get 48 equals 16.7 plus x. Take away 16.7, and we get 41.3 is equal to x. So that means that base 2 must be 41.3. Now if we check it out, we just need, okay, so if we check it out though, if we take 41.3 and 16.7, that adds up to 48, and 48 divided by 2 is 24, so it checks out. Let's look at number 6. In the figure, FC is the mid-segment. Okay, so this is same idea. This trapezoid is flipped upside down compared to the other one. Exactly the same pattern. X plus 14.4 divided by 2 has to come out to be 22. Multiply both sides by 2. X plus 14.4 equals 44. Take 14.4 away from both sides. X is equal to 29.6. And they're not giving us units to have to worry about. So X is 29.6. So if we check it out, 29.6 plus 14.4 adds up to be the 44. 44 divided by 2 does give us 22. So it works out. Now another shape that we have, quadrilateral shape, is a kite. And kites have lots of special properties. A kite is defined as having 2 consecutive pairs of congruent sides. So it gives us this classic kite shape that we all know. So here's a consecutive pair of congruent sides, and then here is another consecutive pair of congruent sides. So without a lot of work, we can actually prove things about these pairs of triangles being congruent and these pairs of triangles being congruent, which gives us congruent angles here. Another thing we should talk about vocabulary-wise, this long diagonal we call the major diagonal. And this shorter diagonal we call the minor diagonal. And you'll see this in other figures too, like as we go through more shapes. The short one is the minor, the long one is the major. Major axis, longer axis, minor axis. Ellipses have a major axis and a minor axis, and so on. So get used to that vocabulary. So lots of properties about kites. And also more stuff. Okay, vertex angle. The angle at the top of the kite is the vertex angle. You can't get vertex in there. Vertex. So this is the vertex angle, and this is also, I call this a vertex angle too. And these are non-vertex angles. That's a non-vertex angle, and this also is a non-vertex angle. The non-vertex angles in a kite are congruent. The major diagonal, the long diagonal, bisects the minor diagonal. So this major diagonal here bisects this shorter diagonal. So that's why we can mark it as this piece is congruent to this piece. Also, it is a perpendicular bisector of the minor diagonal. So the major diagonal is a perpendicular bisector of the minor diagonal. The arm angles, or the non-vertex angles, are congruent to each other. Also, the major diagonal bisects the vertex angles. So this angle C is bisected by the major diagonal, and this angle A is also bisected by this major diagonal. So we have a kite with consecutive pairs of congruent sides. The major diagonal is the perpendicular bisector of the minor diagonal. Perpendicular bisector puts the right angle in there, and also the non-vertex angles are congruent to each other. The major diagonal is an angle bisector of the vertex angles, which would be A and C, and we already had that the non-vertex angles are congruent to each other. So all that is carried by something being named a kite, or something being a kite in our geometry. So let's see. So a kite, a convex quadrilateral with exactly two distinct pairs of adjacent congruent sides. I call them consecutive congruent sides. Its diagonals are perpendicular bisectors. Well, its bisectors are perpendicular, and the major diagonal bisects the minor diagonal. And exactly one pair of opposite angles is congruent. One pair of opposite angles. And I would just write this as non-vertex angles are congruent. Okay, so let's see what else we got going on here. These questions. So if KLMN is a kite, find the measure of angle N. Let's see here. So KLMN is a kite. So let's see. Find the measure of angle N. So this is what's going on. Because this is a kite, we know that these angles are congruent to each other. Let's call it, each one of these measures X. And because it's a quadrilateral, all of these angles need to add to 360 degrees. Remember, we got our n minus 2 times 180 formula for the sum of the angles. 4 sides take away 2 is 2. 2 times 180 is 360. So if I add these up, subtract from 360, I'm going to divide by 2, and I'm going to find the measure of angle N. So 71 plus 52 is 123. 360 minus 123 is, what, 237? And then I'm going to take 237 and divide it by 2, and I'm going to get 118.5. So 108. So the measure of angle N equals 118.5. So again, sum of the inside angles has to be 360. 2 of those are congruent. Let them be x. 2 x's plus 71 plus 52 equals 360. Combine like terms, and 360 take away 123 divided by 2 comes out to be 118.5. Let's look at the next one. ABCD is a kite. Find the measure of angle A. So here they're giving us that this is a 90. Again, because it's a kite, those non-vertex angles are congruent to each other, which lets me jump this 107 degree measure down there. Now altogether, these need to add up to 360 degrees. So now I have 107 plus 107 plus 90 is equal to x. So 107, 90, 14 gives me 304. 360 minus 304 gives me 56 degrees. The measure of angle A equals 56 degrees. So those little degree marks in there. Let's move on. Find the following values. Find the following values for kite ABCD. AB. Let's see what we got. So again, these are right angles here, because this major diagonal is perpendicular bisector of the minor. These two triangles are congruent. We got like side angle side or hypotenuse leg. Well, side angle, well, hypotenuse leg bunches of ways. So these two pairs are congruent. These two pairs are congruent. Okay, what I'm going to do on this problem is to make these numbers a little bit easier to deal with. Let me zoom in a little bit here. So what I'm going to do is I'm going to take 6, since 6 is a multiple of all of these different side lengths they give us, I'm going to kind of scale this figure down a little bit to make the numbers simpler, and then put the 6 back in. So I'm going to take a 6 out of all of these to begin with. So I'm going to deal with this like it's a 1. This is going to be a 2. This is going to be a 2. This is going to be a 4. And let's see what we can do with these triangles. So these two are right triangles. So with the Pythagorean Theorem, we can actually look at this as being a 1 and a 2, and we want to find out what this AB length here is. We'll call this just AB for the length. So we got 1 squared plus 2 squared equals the length of AB squared. Take the square root of both sides. This is really just the Pythagorean Theorem. We have AB is equal to the square root of 1 plus 4, which is square root of 5. So this length here is actually the square root of 5. And because these two are congruent, this one over here is also going to be square root of 5. Now they also want us to find CD. Let's do the same thing to find CD. I'm going to use these smaller numbers. So actually now, the actual length of AB, remember, we took a 6 out to make these numbers smaller. I need to put that 6 back in. So AB is actually 6 root 5. Then I want to do the same thing down here that I did up there. So now I'm looking at this triangle here. And again, this is a right triangle. And we have a 2, and we have a 4. Remember, we already took the 6 out. So now we got 2 squared plus 4 squared is equal to this distance squared, which we'll call AD squared. Take the square root of both sides. AD is going to be the square root of 2 squared, which is 4, plus 4 squared, which is 16. So we get the square root of 20. So AD is the square root of 20. Now square root of 20 can be simplified. Since 20 is 4 times 5, we can actually call this 2 square root of 5. So we got 2 square root of 5, or square root of 20. So the length of CD, get rid of this protractor here. The square root of, or the length of CD is going to be 6 times this square root of 20, or 6 times 2 root 5. So 6 times 2 root 5 is going to be 12 square root of 5. So that's going to be the length of CD. Square root of 20 is not the best answer. 12 root 5 is simplest radical form, and 6 root 5 is already in simplest radical form. Now it wants to talk about the perimeter here. I could do the same thing with these lengths here and then multiply everything by 6. We got square root of 5 plus square root of 5. That's 2 square roots of 5 plus, well, let's see, AB. So we got 6 square root of 5 plus another 6 square root of 5, because this other side is congruent to it. So we actually have 2 6 square roots of 5 for the AB and BC part of the perimeter, and then we actually have 2 of these 2 square roots of 5 or 2 of these 12 square roots of 5 for the other 2 sides, which are the AD and the CD side. So altogether we get 12 square roots of 5 out of this part, and we get 24 square roots of 5 out of the other part. So we get 36 square roots of 5 for the perimeter. Now in terms of a decimal number, if you look at square root of 5 as being like about 2.2, it's close, something close to that. 2 times 36 is 72, and another 0.2 times 36 is going to be another 7.2, so it comes out close to 80. You got like 72 plus 8, somewhere around close to 80 would be the length if we were to go into decimals. Okay. Okay, let's look at this next part here. In looking at this, okay, I see this 6-8 pattern, and we know, again, because this is a kite, that this is a right angle. So what we have is a right triangle that has an 8 with a 6. Now this sets up a special pattern for right triangles called a 3-4-5 Pythagorean triple. I kind of turned it sideways. So if I kind of match it up here, take a 2 out of the 8, you get a 4. Take a 2 out of 6, you get a 3. And this sets up the most basic triangle that we can make out of integers. 3, 4, 5. 3 squared is 9, plus 4 squared is 16. 9 and 16 is 25. Square root of 25 is 5. So if we have a 3 and a 4 set of legs in a right triangle, the other side has to be 5. So now since this was half of the 6 and the 8, this is actually going to be double the 5, which is going to be a 10. So I can just recognize, without having to do any extra work, 3, 4, 5 Pythagorean triple means that has to be a 10. Now that's not going to work for this one, but I can simplify the numbers. So if I take, say, a 4 out of each of these, which is the lowest, the greatest common factor, well, really 8, I can do a 1 and a 3. I didn't see that before. So if I take an 8 out, I can actually turn this into 1 and a 3. So this is really 1 times 8 and 3 times 8. But in terms of the triangle, doing the quadratic formula, or the Pythagorean formula on it, we've got 1 squared plus 3 squared is equal to xy squared. So 1 squared plus 3 squared equals xy squared. Xy is going to be the square root of 1 squared plus 3 squared, which is square root of 10. So this length is going to be square root of 10. But remember, we took an 8 out, so this is going to be 8 square root of 10. And this is going to be 8 square root of 10. So I kind of made the number smaller and then put the 8 factor back in again. So altogether, the perimeter, well, Wx is going to be 10. Zy is going to be 8 square root of 10. Now, if you look at square root of 10 as being like 3.3, maybe it's more like 3.2. 8 times 3.2 is going to be about 24, plus another 1.6, so it's going to be somewhere around 25. And then the perimeter, we're going to add all these up. We've got 20 plus 16 root 10. So that's the exact answer. Again, if you look at root 10 as being about 3.2, you've got 48 plus another 4, so you got about 52, 62, you got about 72. So decimal-wise, it's going to be close to 72, but exact answer-wise, 16 plus, or 20 plus 16 root 10.